Hello, in this video I'm going to talk about some strategies for assessing normality. So let's say that we have some raw data and we want to know if the data is normally distributed. Of course, one way that you can do this is to construct a histogram and then look to see if the shape is roughly, bell-shaped. But we have another method which is called a normal probability plot. And so the way that this works is that we consider our data and what it would look like if it were normally distributed. And so we plot the raw data against a z-score. We call it an expected z-score. And that would be a z-score if a data set of the same size were normally distributed. We plot those against one another and then look to see if there's a linear correlation. So I'm going to give you a strategy or outline a strategy and then show you an example. The steps for constructing a normal probability plot. The first thing you want to do is to arrange the data in order least to greatest, so in ascending order. And you'll assign an index, so you would number the data 1 to n, where the n is however many data points you have. And next you'll want to compute for each one of these, compute for each one of these, f sub I. And there's a formula for this where we take I, which is our index number, so for each number 1 through n we'll have to do this. We take the index number and subtract 0.375 and we take n plus 0.25. And then for each of these values, we'll find the corresponding z-score for each f sub I. And then lastly, you will plot the observed values of your raw data on the horizontal axis and the expected z-scores on a vertical axis. So notice that these values f sub I, there's nothing in this formula that depends on our actual data, just the position of the data. So this formula takes each position and then assigns it a value from 0 to 1 and a kind of a and then we'll use those values to find the corresponding z-score. This will be a little bit clearer when you see it in an example. So let's look at some raw data. So here I have some data from a business. These are the number of customers they see in a day. And so here's my raw data. There are, let's see, I think there are 25 observations, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, yeah, 25. So I've taken the raw data and here I've put it in order from least to greatest, so it's in ascending order, and then I've numbered the values 1 through, and let's see, there were 25 in total. So here's the data in ascending order. Now, for each of these values, I need to calculate f sub I. I take the index value, that's the value in this case for the first data point, it would be 1, subtract 0.375, and then divide that by n plus 0.25. And here's the result. And then I can look up the expected z-score for this value and find that that's 0.196, negative 0.196. So if you're thinking about your standard normal curve, and so we've got 0 in the middle. And what I'm doing, I'm saying, what's the z-score that corresponds to an area of 0.0248, and I'm finding that that z-score would be negative 1.96. So as we calculate these values, you'll notice as you proceed with this that these values are going to increase each time, and so as we move higher and higher up the list when the data are in ascending orders, we'll be shading more and more area under this curve, and eventually we will move over to the right hand side and start shading everything to the left. So and eventually we'll get close to having 100% of our data and the corresponding z-score over here. Now these this is symmetric, and really we only need to do this for half of the data, and then we can just switch these z-scores from negative to positive. So something I want you to consider that might help you understand how this works. Remember that if data is normally distributed, then the mean and the median should be equal to one another. So if our data follows a normal distribution, the value in the center here, the mean, would be the median. And so in this data set we had 25 values, and so it's easy to find the median. We want the value that splits the data in half, so that would be the data value in position 13. So that leaves 12 values less and 12 values higher. So this value in a standard normal distribution would be should have a z-score of 0, and it should split the data 50-50. And so if you take 13 and subtract 0.375 and then divide that, so I'll just show you here, if we take 13 and subtract 0.375 and then divide that by n plus 0.25, our n is 25, so this would be 13 minus 0.375 divided by 25.25. Notice you'll get 0.5, and if we use our inverse norm function to look up the corresponding z-score, so for 0.5, you know that you're going to get 0. And so we could do that for all of our data, but my point was in saying that if we do it for one half, the second half is a freebie. Notice here that for the last data point, the one in position 25, the F value is 0.9752 and the z-score is positive 1.96. And notice for the first value of my data set, I had a z-score of negative 1.96. So one of those values, if this is normally distributed, would be down here on the left hand side, and one of them here is over on the right hand side. So this would be my first data point, and this would be my 25th data point, and then this represents the 13th data point, the one in the middle. Now of course if you had a different sample size, that wouldn't necessarily be position 13, and that wouldn't necessarily be position 25. This would just be whatever your highest value is, and this would be the position of your median. So, alright, now how do we use this for a normal probability plot? Once we have these values calculated, we're going to do a plot on an XY grid where this is our X value and this is going to be our Y value. So one way to do this in your calculator is to use a list 1 and a list 2. There is a shortcut in some ways. Let me just show you. If I go to my stat menu, I put in each of my data values into list 1. So here you'll see 21, 21, 22, and so forth. So in list 1, I put the values in order. I didn't have to do that for this purpose, but it's going to come in handy later to have entered these in order. So if I want to generate the plot where these values are on the x-axis and these are on the y, I can simply go to my stat plot menu and make sure all the other stat plots are turned off, but leave your first one turned on and hit enter. So this is on. And for the plots type, move your cursor to the very last option. And so we don't want a scatter plot, but we want this normal probability plot. And when you select that, it'll say your data list. Mine's in list 1. And I want my data on my x-axis, and then you could use whichever of these markers you want. So once you have those settings correct, you can go to zoom and then choose option 9. And this is what a normal probability plot looks like. So the line that's in the center here represents 0. So things below this line have a negative expected z-score, and items above this line have a positive expected z-score. And if we're going back to our list here, this point here where I have a 24 and a 0, somewhere in here there is, this must represent a 24, and there's a point that's right on that axis, and that represents this ordered pair, 24, 0. This point on the normal probability plot represents this 21 and negative 1.96, and this last point represents the last ordered pair, 26 and positive 1.96. So what we're looking for in a normal probability plot is to see whether there's a linear relationship. And sure enough, it looks like there is a linear relationship between these points. Now, here's the downside to a TI-84. We are not able to calculate the correlation coefficient directly from this normal probability plot. So for that reason, I'm going to go back to my stat menu and show you what I've done. So in list 2, and this was kind of tedious, I actually completed this table. So I filled in all the values and found the z-scores using my inverse norm function, and I put all the data from this column into list 2 in my calculator. Now again, I'll remind you, I really only had to calculate the z-scores for the bottom half. I know that if this is 0.10, that this value would be negative 0.10. And this is positive 0.20, this would be negative 0.20. So I got to just do half the work, really, and then fill in this value. Now, this time, I'm not going to use the normal probability plot feature. I'm actually going to just use a scatter plot. So I'm going to go back to my stat plot menu, and this time I'm going to choose the scatter plot. So I've changed my selection there, and notice the prompts changed. My x values are in list 1, my y values are in list 2. I'm going to keep the same mark, and go back to zoom, and option 9, and you know it looks the same. But the advantage of this is now I can go to my stat menu, and under the calculations menu I can find the regression line. So option 4, and I'm using list 1 and list 2, and so I find that my regression equation, the slope is 0.6432, and my y-intercept is negative 15.3588. And this is what's particularly helpful, is that my correlation coefficient, R, is 0.9654. So remember that if we have a value of R that's either close to positive 1 or negative 1, that's indicative of a strong linear correlation. In this case, it would be a strong positive. Now, is it strong enough, though, for me to say that there is a linear relationship? For this, I want to look up a critical value. There are tables for this, and in fact, I have one very handy. It's on the other side of this paper. In this table, I look up the sample size to find the critical value. And this is kind of small, but I had 25 data values, and that says 0.959. So my critical value is 0.959. So if R is greater than the critical value, we say that the data is normally distributed. So again, let's go back to the scatter plot. So zoom. So the closer these are to a straight line, the stronger is the evidence that this is normally distributed. Okay, so let me show you though what other normal probability plots look like outside of the TI-84. Here are two examples. So oftentimes a normal probability plot will include the regression line. So in the first line here, so these data points are the original data values. In this case, they're plotted against a percent. So like the 50th percentile for as far as a z-score, that represents a 0. So these would be our positive z, and these would be our negative z. So the scale is a little bit different here, but the look of the graph is the same. So notice that these data points, they do not always stay really close to this line. In fact, they kind of squiggle around it. Some are close, like right here in the middle, but others are further away from the line. So that's the center line that I'm referring to. To help us know, if these are staying close enough, many probability plots will include these boundaries. And so these boundaries always have a slight curve to them. And so if all of the points on your scatter stay within these boundaries, you can say that it is normally distributed. Now in this case, I have some values that are definitely out of bounds. And so I would say that this is not normally distributed. However, let's look at this other example. Here's the regression line, and there's some variety. Some of the points are very close to it here in the middle, but then some are further away. But notice all of the points in the scatter are inside the boundary of these curved lines on either side of the regression line. So I would feel comfortable in saying that this is normally distributed. And of course, if we want to be certain, we could always calculate R and compare that to a critical value. In this case, I'm going to assume that R would be less than our critical value, and here that R would be greater than the critical value. These, I believe, were created using software called Minitab. Your TI-84 calculator is not quite that sophisticated. Now, if I wanted to, I could add our regression line at least. Let's see, where did I put that? Let's see, my regression line was 0.6432x minus 15.3588, and then let's go back. So I can at least do that part, but I won't have those nice curved boundary marks. All right, so one other thing I want to remind you of, if we go to our stat menu and do some calculations, the first option is our one variable statistics. So if I run this on my original data, which is in list 1, I can find that my mean, let's see, make sure I'm showing you here, the mean is 23.88, and the sample standard deviation is 1.45. So if I wanted to get a picture of what this distribution looks like, I have information that says it is normally distributed. So I might want to picture that. So I can draw a normal curve, and in this case I can say that the center here is at 23.88. I'm going to do some rounding here, and let's round this to the nearest whole number and say that's 24. and I want to round this to 1.5 because I'm just using this as a tool for myself and I want to make math easy. So that's the X bar is 24 and each standard deviation is 1.5. So this would be 25.5 plus another 1.5. This would be 27, 28.5. This would be 22.5, 21, and 19.5. So the normal probability plot, together with the correlation coefficient compared to this, leads me to believe that this data is normally distributed. So I feel comfortable, using a normal curve to represent this data. And furthermore, I can now, if I want to, use percentages from the empirical rule and say that, remember, these were the number of customers seen per day. So I would expect on 68% of the days that you'll see between 22.5 and 25.5 customers. 95% of days, this business will see between 21 and 27 customers. And you can go back and compare that to your original data and see how accurate this is. Now, in the original data, all the values were between 21 and 26. So, in truth, it was 100% or between here. So this is not exactly normally distributed, but it's pretty close. So we didn't get a perfect correlation here. There were some values. If we go back and look at our, not all of the points are exactly on this line. There's some variety around the line. So, it's not a perfectly normal distribution, but really close. These are going to be good for approximations. So there we go. That's how we're going to assess normality using a normal probability plot and comparing a correlation coefficient to a critical value. Hope that helps. I'll see you next time.